Welcome to Millrock Technology. Today we're going to be discussing LyoPAT, Millrock's freeze-drying process analytical tool. What is LyoPAT? LyoPAT is a heat flux measurement system that allows us to monitor the key process parameters for a much better understanding of the freeze-drying process. Because it's a heat flux measurement, it's in situ, it's a direct measurement. It's continuous and real-time. It's non-invasive and non-interrupting. It's batch size independent, so it works with one vial, a small batch of vials, all the way up to a full load. It works for the entire freeze-drying process, including the freezing steps, primary drying, and secondary drying. It's critical to understand that because it works in the freezing process, it's the only known PAT tool for the freezing process. And it's freeze dryer independent. Little baseline, the difference between temperature and heat flow. Temperature has always been considered the key process parameter. However, in fact, it's heat flow. For example, during freezing, as the ice crystals grow, the temperature of the material doesn't change. It rises up to near 0 degrees and stays there. However, the heat flow can change pretty dramatically during this period of time. And as it changes, the ice crystal formation changes. So it's very critical to understand how that heat flow is occurring to control your ice crystal structure to generate the best structure for primary drying. During primary drying, as the dry layer builds up, the heat flow also changes. And that changes the characteristics of sublimation. Therefore, heat flow provides all the necessary information to analyze and control the process. Take a look at where the heat flux sensor is placed. It's placed on the shelf between the vials and the shelf. In this location, we actually are measuring the heat flow going into the vials, the shelf surface temperature, and the product temperature. That gives us a direct measurement of the thermal conductivity of the vial. In addition, it gives us a direct measurement of the heat flow, which gives us more information on things like mass flow. If we take a look at what's SMART and how SMART works, it's an MTM pressurized test where the isolation valve is closed between the product chamber and the condenser. The pressure is allowed to rise for 25 seconds, and a significant number of calculations are performed to determine some of the critical process parameters. Those calculations are all filled with estimates and assumptions. LyoPAT, however, because we're doing a true in-process measurement, we're truly measuring the shelf temperature. By the way, we're measuring it at the shelf below the product. SMART measures the shelf temperature at the inlet to the shelf, which is several degrees different. We're measuring the heat flow with LyoPAT, and if we have a thermocouple, we measure the product temperature. That gives us directly a measurement of kV. If we already know kV, we don't need a thermocouple. We can actually calculate the product temperature based on the known kV. Some of the limitations of SMART include it's an intermittent measurement. It's performed infrequently. To get the critical process parameters, calculations are done. They're actually not measured. And that's being done through multiple equations with assumptions, which generally leads to some inaccuracies. It requires at least one full tray of product, and it doesn't work for all products. For example, it doesn't work for high solid content. In this diagram, we're showing the way that the heat flow measurement gives us information on the thermal conductivity of the vial, and that allows us to calculate the product temperature if there is no thermocouple. We can also directly determine the mass flow or the mass transfer going into the product, which is directly related to the sublimation rate, the cake product resistance, and even predict end of cycle time. Some of the things you can see with heat flow, which you can't see with any other methodology, is, for example, the end of supercooling when the product is ready for nucleation, the nucleation events that occur during freezing, and when freezing is done. When the heat flow goes up towards 0, we know that our product is done crystallizing. We can also measure the end of primary drying, and determine any changes in performance during the sublimation or freezing processes. For example, if a vial changes or a fill changes, the heat flow is going to change pretty dramatically. Some of the LyoPAT technologies that are used are the heat flow measurement, which we also call AccuFlux, and we combine that with controlled nucleation. This allows us to develop different freezing protocols to enable the user to identify the best protocol to develop the best cycle for primary drying. It's critical to understanding how to optimize any freeze drying process. Nucleation stations available from a small system to larger systems and production systems. LyoPAT, if we take a look at the freeze drying cycle, LyoPAT works in conjunction with what they call controlled lyo for controlled nucleation. One of the first key concepts to understand is that controlled nucleation only nucleates about 10% of the available water in your product. Therefore, 90% of the ice crystal formation occurs after the controlled nucleation event. So it's all post-nucleation. So just having controlled nucleation is not enough to produce an ideal structure, ice crystal structure, for your primary drying process. SMART works intermittently throughout the primary drying process. When we take a look at Millrock's technology, freeze booster is used to develop the controlled nucleation event. And then we use our AccuFlux to actually control the heat flow going into the process to control the ice crystal growth. And then during primary drying, we add our AccuFlux. And when combined into LyoPAT, we can see the effect on primary drying. We have a very long primary drying cycle here. In an unoptimized cycle, after optimization, we dramatically have reduced the primary drying cycle. Ways to use LyoPAT include directly measuring KV. You can measure the effect of changing the application variables. For example, if your pump is not working properly and it's not cooling the shelf properly, that would be the fluid pump. You could actually see that change because the heat flow would change. If the vials have changed or the fill has changed, you can see that dynamically in the process. You can determine the effect of freezing methods on primary drying, which is wonderful. You can do ramps, you can do holds, you can do controlled nucleation with or without controlled heat flux, and determine what the best ice crystal structure is for your product. You can characterize your existing freeze dryers. You are developing truly optimized protocols. These are not protocols that are conservative. These are actually optimized based on the product temperature. And we typically allow you to set the product temperature at some temperature below the critical temperature. You can develop transferable protocols based on the thermal conductivity of the vial and heat flow, and develop a design space in a single run. So what kind of information does LyoPAT give me? Well, during freezing, I can see with the percent frozen by nucleation. We can display the freezing progress through the stages of freezing, the end of supercooling, the end of freezing, the energy for cooling, the liquid, nucleating the ice. During primary drying, we directly measure KV, calculate the cake resistance, measure product temperature or calculate product temperature, measure the heat flow, total heat removed, the mass flow during primary drying, the mass removed, percent dried. We can determine the end of primary drying and the end of secondary drying as well. For controlling the process, we can control the supercooling process, the nucleation process, the post-nucleation crystal growth. Again, nobody else has this capability. We do automatic step advancements based on the heat flow, the steady state heat flow. For example, if you choose to freeze your product using a protocol, when it's actually stabilized, we would automatically advance rather than waiting for a period of time. Same thing with primary drying. We can actually control the product temperature based on the critical temperature and advance into secondary drying when we hit the end of primary drying as well. And last but not least, we can do a design space in a single run. If we take a look at this chart, which I won't sit on too long here, you can just pause your video. Here are some of the things that LyoPAT does versus Smart. Again, some of the major differences here are it's in situ, continuous. It works during the freezing process, the primary drying process, and the secondary drying process, and it produces a truly optimized process, integrates with controlled nucleation as well. Here's an example of optimizing a protein product. We took a 2% concentration product, 21 ml fill in a 50 ml vial. The original processing time developed on another system was 121 hours, and it included an annealing step. If we take a look at the actual freezing cycle here, we took our shelf temperature down to -5 degrees and allowed the product to stabilize. The red line here is the heat flow. So the heat flow changed dramatically and then stabilized out. Once it was stabilized, we developed a controlled nucleation event, which is what you see here, a huge drop in the heat flow. And then we controlled the shelf temperature to control the heat flow at -600 watts per square meter. What this controlled heat flow does is give us a very uniform crystal structure inside the vial. So the nucleation freezes about 10% of the product, or 10% of the water, gives us a very uniform structure across the batch, and controlling the heat flow after nucleation gives us a very uniform structure inside the vial. Nobody else can do this. Now that the product has been frozen, we can take a look at the primary drying cycle. Here we have the capacitance manometer and the Pirani up on the top. It's the Pirani here. You can see at the end of the run, at the end of primary drying, the Pirani drops pretty dramatically at the end. That shows that we have a really uniform cake crystal structure. We were using product temperature control to feed back to the shelf, so you can see the shelf temperature went up to 10 degrees and dropped down over a period of time, and then finally stabilized out at around 0 degrees. Here, some of the thermocouples had come out of the product, and we made a correction that's now been taken care of in the software. So this is the final run for primary drying time. And we dropped into secondary drying, and you can see the shelf temperature was raised to 30 degrees. The heat flow went up pretty dramatically. The Pirani went up, so you can see that we're releasing some moisture. And the heat flow and the Pirani pretty much track each other. The end result of this was that we reduced the time of the cycle to 64 hours total, including freezing, which is a 55% reduction. So the original cycle took 121 hours. The improved cycle using LyoPAT took 54.1 hours. A significant reduction in primary drying, in process time in general, and a much better product. The residual moisture content was 0.61, plus or minus 0.4%. If you'd like any more information, please contact us here at Millrock Technology. We look forward to serving you.